let's consider an example. Suppose we have a fractional order transfer function. How can we check the stability of the system? For this system, we can see that if we want to convert it into a commensurate order system, we must introduce a lambda like this. Lambda equals to s to the power of 0.001. Suppose there isn't any I think the greatest common divisor is 0.001. So you have to use a notation like this. And if you use this notation and you want to transfer the original one into the transfer function of lambda, what you have here is lambda to the power of 3,501. The order is too high. It will correspond to a polynomial with a degree of more than 300. So it might be too complicated. It is possible to solve in Matlab, but it might be too complicated. So we'd better, I think for this case, we'd better introduce an operator, one like this, so we can perform, we can rewrite or we can approximate the original transfer function like this in case we do not have a polynomial, the order is too high. So we can approximate the original system like this. However, since there is a simplification or approximation, I'm not quite sure whether they still gave the very correct result. I think Lian is working on this. So I think he's got a positive result on this one. He may find the bond. So on how much the error might be. So we can approximately analyze the approximate the original transfer function like this. And for this term, we can approximate 1.8 like this. And then we can enter the original transfer function. This one is done automatically by the code. And we can enter the original transfer function using the code like this. And in fact, the system model then may be expressed. The system may be approximated automatically by the code itself. So by calling this function, we can easily find that the value of k, it might take, well, I think I still use the 3,000 degree of polynomials, so it might take a long time. Last time when I talked the problem with Dr. Lee, I think I changed it. I didn't use the approximation. I didn't use the approximation here. So I still use lambda equals to s to 0.001. So it may take some time. And if you are using the approximation like this, you may get the result in a few seconds.
So did you try to put the G? The capital G is an FOTF object.
Yeah.
And if you put a normal and LTI object, will it work?
I don't think so.
Okay. So.
Yeah.
It's good.
You mean that there is a
backward
integer order transfer function, and I try to express it in fractional order. It works.
It works?
Yeah.
Okay.
And in fact, I have defined the function FOTF in the directory TF. And if you have integer order system, if you call FOTF function, it will be converted into fractional order transfer functions automatically.
Okay.
Well, it may take.
So You mean to say if I gave an approximation of a fractional order transfer function and call this, it will give me that?
Yeah.
Oh, that's good.
It's still running. So I will talk on these topics. And this function will return the value k, which is 1 or 0, means stable or unstable. And also the alpha. In this case, alpha should be 0.001 instead of the one I said earlier, the approximate one. And those, I'm not quite remember what are those parameters. When we get the result, I will say something about it. Well, the system is stable for it, and the value of alpha is 1 to the power 10 to the power minus 3, which is the same as the one I used. And apart from the results, if we go back to the Matlab display, we will have something like this. And these are the poles of the system. The poles of the polynomial, the zeros of the polynomial actually. And if you zoom this part, this is the line for alpha times pi over 2. So you see that in this area there isn't any pole. So the system is stable. All the poles are distributed in the other area. And it is quite interesting to note, I do not know why. I talked with Dr. Lee and I don't think he got the answer also. The poles are located almost in a circle. This is quite strange. I cannot give explanations. If you zoom it, it is not necessarily on the circle. It is quite closely distributed to a circle. Suppose this is a circle, the poles may be distributed like this. So you see that they are almost given in a circle. I do not know why. Quite interesting to know that. So in this way, we can check the stability of the system.
So the line is an alpha pi by 2, right?
Yeah.
0.001.
Sorry, and alpha is 0. Yes, this is the value of alpha, and the line with a slope of pi over 2 times alpha.
So that means like the poles have to lie in a really small region for the system to be unstable.
Yes.
Yeah. If there are some poles located under this line, then we say it is unstable.
So then does that mean
And for this example, it happened that all the poles are over this line, so it is stable.
So I'm thinking, does that mean that achieving stability for fractional order systems is easier than integer order because they have a bigger area?
Yeah. If alpha is smaller than 1, if alpha is larger than 1, smaller. If alpha is larger than 1, the stability region is like this. Right? So for integer the system, if alpha equals to 1, it is the vertical line, the y-axis. So for alpha is smaller than 1, so it should be instability. Unstable region should be smaller.
So for alpha equals 4, it will never be stable.
And you can recall the integer order systems if you have, I think, it will not stable because there are terms missing. So I think the result should be consistent with the integer order problem.
It's true. It's very
Well, this is the stability analysis.